In this lesson, this is called falling body problems, and it's called that because it's talking about things that are dropped or thrown downward, so things that are accelerating due to gravity. And for our purposes, acceleration due to gravity near the surface of the Earth is negative 9.8 meters per second squared. It's a negative number because it's downward. The acceleration, it's accelerating towards the Earth, so downward. We can use this fact plus other given information to solve problems involving free-falling bodies. We're neglecting air resistance here. In physics, a formula that would be learned would be this height function, and the position function when dealing with objects in free fall close to the Earth's surface is h of t. H really representing the height after a certain amount of time is negative 4.9 t squared plus v sub 0 t plus h sub 0. Now this sub 0 is an important subscript. This is talking about the initial velocity, the initial height, and even t sub 0 here, so I'll mention this now, is the exact moment the object is put into motion. It might be dropped or thrown or projected. We'll be deriving this function in several of the examples because if we know the acceleration, we can find velocity and position functions. So again, t sub 0 represents the exact moment that the object is put into motion. So let's start with this first example. An object is dropped from a height of 2,000 meters. Begin with the acceleration function and develop the position function. And then we're going to answer the question, how far above the Earth will the object be 20 seconds later? So a few things we need to recognize here. It does say start with this, the acceleration function. The acceleration function is a of t. So the acceleration near Earth surface is negative 9.8. Now, how do we get it? It asks for the position function. Well, to get the position function, what we're going to do is we're going to find the velocity function. And the velocity function is, if you remember, the integral of the acceleration. So this is going to be negative 9.8 t plus c. And now there's something important. There's an important word here that we need to recognize. We see the word dropped. And dropped tells us about the initial velocity. If we have something that's dropped, that means there's no initial acceleration. So dropped means v sub 0 is equal to 0. So the initial velocity is equal to 0, which tells us when the time is 0, the velocity is 0. So what we're going to do here is we're going to notice we can put this in here. So our velocity is 0 when our time is 0, which means in this case our c value is 0. And so we can replace this c. We know our velocity function is just negative 9.8 t plus 0 because our c is 0, but we don't need to put that. We want to get all the way to the position function. So position function, which we'll call h of t. H of t is the integral of velocity. So this is going to be, we would this would be a t squared, which means we would put a half out in front of here. So half of 9.8 is 4.9. So negative 4.9 plus t squared plus c. The 2,000 meters, it's dropped from a height of 2,000 meters. That is our h sub 0. That's our initial height. And so that tells us when the time is 0, the height is 2,000. So when our time is 0, our height is 2,000. So we know 2,000, our height is 2,000 when our time is 0, which means c for the height function is just 0. And so we can say, we developed the height function or position function. H of t is negative 4.9 t squared plus, I'm sorry, I wrote this wrong. C is not 0. This is 0, so C is 2,000. I apologize. And so plus C, which is 2,000. And so we found the position function. How far above the Earth will the object be after 20 seconds? Well, that's at a time of 20 seconds. So the first answer is this right here. Second answer is we're going to put 20 in here. So h of 20 is negative 4.9 times 20 squared, which is 400, plus 2,000. And we want to multiply this out. I believe this is negative 40. Negative 1,940. Let's go ahead and multiply that. We got 4.9 times 400. And we move the decimal over one place. So we get 1,960. So this is negative 1,960 plus 2,000. And so this thing is very close to the ground after a 2,000 foot drop. It is at 40 feet. So the height after 20 seconds is at 40 feet. That's the second answer to the question. So some important things: ball being dropped or object being dropped means the initial velocity is 0. The height is our initial height, which we used here. That was our height when the time was 0. Moving on to the next example. Now a ball is thrown downward with a velocity of 40 meters per second. That automatically tells us our initial velocity is negative 40, and we'll talk about that later. In fact, I should write that as v of 0 is 40, negative 40, and it's negative because it's thrown downward. Our initial height, so h at time 0 again is 2,000. Begin with the acceleration function. So acceleration is negative 9.8 meters per second squared. We want to get the position function for the ball. What will be the position of the ball after 8 seconds? So we're going to integrate to find the velocity function, and that's negative 9.8 t plus c. So we integrated the negative 9.8 to get negative 9.8 t plus c. We know v of 0 is negative 40, so we know our velocity is negative 40 when our time is 0. So that tells us that c is negative 40. And so we can now take our velocity function from here and put in that negative 40. So v of t is negative 9.8 t minus 40. We want to get to the position function, so we are going to integrate this. When we integrate this, it gives us our position or our height, and that's negative 4.9 t squared minus 40t plus c. Well, we know that our height at time of 0 is 2,000, so we know that our height is 2,000 when we plug in 0 for the time. Which tells us that c is simply equal to 2,000. And so our height function turns out to be h of t equals, this function right here, and we're going to put in 2,000 for c. So negative 4.9 t squared minus 40t plus 2,000. And so that's the height function. The next question, what will be the position of the ball after 8 seconds? So we're going to take our position function, we're going to plug in 8. So 8 squared is 64, minus 400 times 8, or 40 times 8 is 320, plus the 2,000. So let's go ahead and calculate this. We need negative 4.9, and we're going to multiply that by 64, which is negative 313.6. We're going to subtract 320, and then we want to add 2,000 to that. And that will give us that our height is 1,366.4. So that is our height after 8 seconds. And this would be in meters. Okay, the next one, a boy stood on top of a building 40 meters high. Should say high, not height. Or, yeah. And threw a stone so that it had an initial upward velocity of 20 meters per second. Begin with the acceleration function, develop the velocity and position function for the stone. How high will the stone go? How long after the stone is thrown will it hit the ground? All right, so again, we're starting with the acceleration function, which close to the Earth is negative 9.8. Our velocity function is the integral of that, so negative 9.8 t plus c. We know the original velocity is 20. That means the velocity is 20 when the time was 0. If we put 0 in for t, we see that gives us c is 20. It's a positive 20 because it's thrown upward, so we can plug that c in. So that was part of the question. It wanted to know the velocity function. We want to develop the velocity function. Now the position function, which we write h of t, is going to be the integral of that, which is negative 4.9 t squared plus 20t plus c. And we want to figure out what this c is, so we look back at the original height. The original height was 40 meters, so the height was 40 when the time was 0. So if we put 0 in here, that gives us 0, and another 0, so 40 equals c. And so our height function is negative 4.9 t squared plus 20t plus that 40 that we found for c. So that was another thing that the problem asked. So we got the position function. How high will the stone go? How high will the stone go? Well, so this thing, it's 40 meters off the ground. It's thrown upward. How high is it going to go? We want to find this height right here. Well, it looks like a parabola. But what we can do, when is this the highest? This is when the velocity is increasing, it stops increasing, then it slows, or it goes down. So we want to find when the velocity is equal to 0. So let's come back to our velocity function, and we're going to plug in 0, because when it's at its highest, the velocity is equal to 0. So 0 equals negative 9.8 t plus 20. We would add 9.8 to both sides, 9.8 t, sorry. And that's equal to 20. Divide both sides by 9.8. And I believe you get 2.04 seconds is when it will be at its highest. How long after the stone is thrown will it hit the ground? Well, hitting the ground is figuring out the height is what? That hitting the ground, the height is 0. So what we're going to do here is we're going to set this equation equal to 0. And we would want to solve that. We could solve that using the quadratic formula. If you work through that with the quadratic formula, you're going to get two answers. So if you use the quadratic formula to solve this, you end up getting 5.6, about 5.6, and negative 1.4 or 1.5. Obviously, we're not going to have a negative time. So how long after the stone is thrown will it hit the ground? Well, it'll take 5.6 seconds. And actually reading that, so we answered that question, but I realized I didn't answer the question from before. The question from before, it says, how high will the stone go? I found when it will be at its highest. I found the time when it will be at its highest, but I didn't find how long it would go. So to find, or how high it will go. To find how high it will go, we know it will be its highest, or its maximum at this 2.04. So we need to put that into our height function and find how high it will go. So we would do h of that 2.04, and you would plug that in, and solve that. So you're going to square it, multiply it here, and when you figure that out, you find that the highest it would be is about 60.4 meters. This comes out to about 60.4 meters is its highest. So we have our two formulas that we were supposed to find. I found the time at when it would be its maximum, and later realized I needed to find the actual maximum height, and it's going to take 5.6 seconds to hit the ground. The last example here, a boy stood on top of a building 40 meters high and threw a stone so that it had an initial upward velocity of 20. So that is similar to this one. Actually, it's the same as this one, so I accidentally repeated the slide, so that is it.